Hello, in this presentation I will talk about the optical efficiency for parabolic trough. My title is Optical Numerical Investigation of a Solar Power Plant of Parabolic Trough Collector. My content is abstract, introduction, design error, mathematical result and discussion, and conclusion. Abstract. Firstly, forward development and improving renewable energies in Algeria is one of the main objectives of this study, especially solar energy, that is an exponential and continuous source of energy. Algerian desert has a large area suitable for agriculture but not connected to the electricity network. Therefore, the construction of solar power plant based on the solar energy concentration has been proposed for the electricity production, which exploited in the rest of the economic sector of Algerian states through the study conducted under real weather data for the day 16th of March in year 2018. An optical characterization of a solar power plant of a parabolic trough concentrator has been conveyed in El Wayed region, Algeria. The geometric and optical characteristics of studied solar collected have been determined, such as the optical efficiency, the local concentration ratio, ATC, and the optical efficiency was determined 78.7%. Introduction. We know the solar energy is one of the most renewable energy sources in the world. It is a solar radiation that can be used in several fields, the most important of which are electricity production and charge the battery, air condition. For good use and more efficient use of solar energy, there are many techniques for solar collector that can be used, including the compound parabolic collector. Parabolic trough is a type of solar thermal collector that is straight in one dimension and curved as a parabola in other two, lined with a polished metal mirror. When heat transfer fluid is used to heat steam to drive a standard turbine generator, thermal efficiency range from 60 to 80%. This figure shows the design for parabolic trough. Parabolic trough power plant use a curved mirrored through which reflected the direct solar radiation into a glass tube containing a fluid, also called a receiver, absorber, or a collector, running the length of the trough, positioned at the focal point of the reflector. The reflector of the parabolic form is one of the most important part of a studied parabolic trough collector. Its purpose is to concentrate direct normal solar irradiance in the focal line. Moreover, the reflector are mirrors that can have different shapes and can be made from different materials, depends on the configuration chosen by the exploiter. Based on what been said previously, the optical losses have a direct relation with the receiver tube, the reflective mirror, and the distance between two successive parabolic trough collector in the same solar power plant. Design error. A parabolic trough solar collector are designed to operate with a single axis tracking. A tracking drive system rotate the manifold about a rotation axis until the sun central radius and the normal opening area are perpendicular. In addition, the collector performance is still threatened by these factors: reflection losses, absorption losses, and losses due to geometric imperfection of the optical system. Now, the mathematical equation. Geometric losses are those that occur due the reduction of the effective area, where they may be manifold or depending on the relative position of the collector between them. The geometric factor is the ratio between the lost area and the opening area. It calculates the effective reduction of area due to abnormal incidence effect, including blockage, shadows, and losses of radiation reflected from the mirror, the end of the receiver tube. When solar radiation is reflected by the reflective mirror to receive tube, part of its length doesn't reach the solar radiation from the reflective mirror, because the solar collector is generally horizontal and single axis of followed by the sun. Thus, during the solar collector, from sunrise to sunset, some of the beam radiation reflective near the end of the reflector outside the sun cannot reach the receiver tube. This is phenomena called the end effect. Okay, in this slide we talk about the equation to calculate the optical efficiency. This equation, it calculates the lost opening area, F, its mean focal distance, W, opening width of reflective mirror, tan incidence angle, and the opening width of the reflective mirror, F, a focal distance. F equal W from 2. Generally, parabolic trough collector terminate with opaque plate to avoid unwanted of dangerous concentration outside the absorber tube. These plates case the blocking or shading of a portion the receiver tube, which indeed reduce the opening area for a plate extending from the rim. This equation can calculate the lost area resulting from shading. W, opening width of reflective mirror, HB, parabola depth, tan incidence angle. This equation, it calculates the total losses in the opening area in terms of incidence angle, focal distance, opening width of reflective mirror, and HB, parabola depth, tan incidence angle. Therefore, find the losses area without taking into account incidence angle into service. AE and AB are summed without including the term tan incidence angle. Finally, the geometric factor is given by the result of this equation to opening area of the solar collector وتان incidence angle. In this slide, the end losses, this is to calculate the end losses factor at both ends of the receiver tube in terms of the curve length of the reflective mirror, the focal distance and the incidence angle can be calculated by focal distance, mirror length وتان incidence angle. In parabolic trough plants, the reflective are arranged in row. The distance and spacing between each two consecutive rows is given by opening width of reflective mirror, cosine incidence angle, cosine zenith angle. Okay, with the zenith angle in a solar power plant of parabolic trough collectors, the value of the distance and spacing between two consecutive row of parabolic trough collector corresponds to the smallest value of cosine zenith angle. As it known, the shadow decreases with increase of the sun height angle, so it increases proportionally with the increase of the incidence angle. Therefore, the factor for the calculation of the rank shadow at low solar altitude is given by 1 minus A shaded to opening area of the solar collector. How calculate the A shaded in next slide? With A shaded is shaded area of the reflective mirror. It can be calculated length mirror, L spaces, cosine tan inverse cosine opening area of the solar collector, tan highest angle. The optical efficiency, the quantity of solar energy absorbed by the receiver tube divided by the amount of direct normal radiation incident on the opening area. The collector optical efficiency can be calculated by PM. It refers primary mirror reflectivity and glass cover transmittance, and AB refer to absorption coefficient of the receiver tube. K incidence angle, its main correction coefficient. How calculate the coefficient correction coefficient in this slide? Where the factor coefficient coefficient correction is one the factor to taken into account in determine the optical efficiency of solar reflectors. It is coefficient that corrects the incidence angle of the solar irradiance arrival into the reflective mirror. This coefficient is called the correction coefficient of the incidence angle modifier. It can determine from equation: focal distance, length mirror, where opening width of reflective mirror, focal distance, tan incidence angle. Result and discussion. I will applicate it the last equation in Excel sheet and have results. All numerical simulation results, as well as the effects of geometric and optical parameters on the evaluation of various optical factors and the optical efficiency of a solar power plant of parabolic trough collector will be presented. This study deals with the optical behavior of the parabolic trough reflected field in a wide region. The altitude is 33 North Algeria. Al-Uwaid area is characterized by a hot and dry desert climate in summer and cold climate in winter, with wind in spring. This region is a desert state rich in agriculture resources, water and arable land, and has a large solar radiation. In March 16th in year 2018 was chosen as a day to conduct this optical examination of the studied solar power plant. This figure shows the day, time, hours with the incidence angle. The incidence angle varies time for the chosen day of study. The angle are different in their advancement from sunrise to sunset. The maximum value for the incidence angle in sunrise and sunset, it's equal 75.31, and the minimum value at the midday at noon 7.79. This figure shows the L spacing with the daytime hours. The distance, the grid distance between the field rows is 1.2 meters. This distance will significantly reduce the amount of thermal losses caused by blockage in a solar power plant with the same dimensions as the studied parabolic trough collector. However, this value corresponds to the time of the sunrise, where the amount of the solar radiation is very weak and doesn't serve the station. This figure shows the incidence angle with some parameter. This parameter total losses in the opening area in terms of incidence angle, AE lost opening area, and AP ratio between the lost area and the opening area, AF ratio between the lost area and the opening area. The result shows, as for the total losses in the opening area, it changed directly with the change of the incidence angle, where it changed proportionally to this angle. This means that increasing the incidence angle value increases the total losses in the opening area. In addition, the maximum value of ALT is 3.23 meters square at the incidence angle of 75.31, while the minimum value is 0.11 at 7.79. And the geometric factor AF has direct relationship with the total losses in the opening area, where it's changed proportionally to ALT. As for the maximum value is 0.83 at the incidence angle of 75.31, while the minimum value is 0.01 at 7.79. This figure show incidence angle with end effect losses. With the end effect losses factor, it's noted that the variation at the end of the absorber tube is adversely affected by the incidence angle. Its value are low at sunrise, then start to rise until moon, and then fall back until sunset. As for the minimum value of end effect factor is 0.81 at the incidence angle of 75.31, while the minimum value is 0.99 at incidence 7.79. This figure showed a relationship between parameter and incidence angle. A shaded effect for shading shading rate. The shaded area rate is directly affected by the change of the shaded area. It increases by it increase, and it decrease by it decrease. This means that the maximum value is at sunrise and sunset 0.99, and its the minimum value between 10 a.m. to 4 p.m. a value about 0. The shading factor resulting from two consecutive rows of parabolic trough collector varies in reverse completely with the shaded area rate, so its value are very low in sunrise. It's equal 0.04, then start increasing until fixed between 10 a.m. to 4 p.m. A value of about 1, and then start decreasing again until it reach the value of 0.04 at the beginning of sunset. Figure 8 and figure 9, it shows the relationship between the optical efficiency with incidence angle and the daytime. We noted the optical efficiency at the midday at 12 p.m. at noon. At the midday of 12 p.m. it's equal 78.7%, and the minimum value at sunset and sunrise 64.3%. Conclusion: efficiency varies with the daylight hours. It's the maximum value at midday, and increase with the efficiency increase with decrease in the angle of incidence. The highest efficiency value calculated equal 78.7 with the incidence angle 7.79 at the midday at the noon. Thank you for your lesson.